How deviant and mean are your data? Introduction and Basics, Part 2, is an episode of the Degrees of Freedom Project videos on chemical and thermal principles. Definitions and additional details can be found in the webpage link in the description. As you recall from Part 1, we had determined that we should 1. Report measured or calculated values with their confidence intervals. 2. Report a measured value as the arithmetic mean of the measurements. 3. Calculate the sample standard deviation of the measured values. However, we have not yet learned how to calculate the confidence interval. In other words, we still don't know how close the mean of our set of measurements is to the true value. We'll need to use the standard deviation to answer that question, and we have a few hoops to jump through to get there. Just as a reminder, for a normal distribution with enough points, 68% of the points will be within plus or minus 1 standard deviation of the mean. That 68% is going to show up a lot, but it always ties back to plus or minus 1 standard deviation in a normal curve. If we had the actual errors and not the residuals, we could calculate the standard error as sigma divided by the square root of n, with the symbol sigma sub mu. But then, we wouldn't need to estimate how close our mean is to the true mean, because we could calculate the true values and have the true mean already. So, we'll use the estimated standard error, calculated as s divided by the square root of n, with the symbol s sub x bar. If the uncertainty in our mean is distributed in a Gaussian fashion, then if we, in our serial sampling, took enough measurements, the true mean has a 68% chance of being within plus or minus the standard error for our sample mean. We typically write this out as a confidence interval. For example, we are 68% confident that the true mean is within plus or minus 7 thousandths of 42.000. The sharp-eared probably noticed that I said, if we took enough samples. That raises the question, how many samples is enough? Let's explore that question while contemplating a pint of Guinness. William Gossett was an employee trying to help Guinness with quality control and developed the statistical distribution for what to do with the standard error when the number of measurements was small. Quality control can only drink so many pints before their judgment becomes impaired. He published the paper under the name of Student, and the distribution has become known as Student's t-distribution. In practice, it's used as follows. We calculate our mean and standard deviation, and then our standard error from the standard deviation. We calculate on a confidence level like 80% or 95%, and whether the true mean could be on either side or only on one side of our calculated mean. We then go to the student's t-test table and use our degrees of freedom, n-1, as the row index, and 1 minus our confidence level as our index. We use the two-sided table, the most common case, if the true mean could be on either side, and look up the value of t. Our measurement is then reported as the mean plus or minus t times the standard error with your confidence level given. You can linearly interpolate in the table if necessary. For example, x bar is 42.000 plus or minus 0.67 with 95% confidence. What are the implications of all this on your measurement making? You can make the mean of your measurements arbitrarily precise by taking a large number of measurements. However, limits of time and money mean that the number of measurements you make has to be limited. What are the trade-offs? The confidence interval, lambda, is the product of students t and the standard error. This plot is the value of t for 95% confidence versus the number of measurements, n. For a given confidence level, t decreases asymptotically. Notice that the decrease in t, and hence the decrease in the width of the confidence interval, from 2 measurements to 3 is by far the largest. That decrease is the reason for the dictum, take at least 3 data points. Beyond 3 points, the increase in accuracy through the decrease in t exhibits the law of diminishing returns. The second figure is the confidence interval, for 95% confidence as a function of n on a log-log scale. It shows, as expected, that for each 100-fold increase in a number of points, you gain 10-fold, or 1 significant digit of accuracy. You, as the engineer, need to decide how much accuracy you need given the time and/or money needed to do a measurement. To illustrate these points, this video displays a histogram and fitted normal curve as we successively add additional samples, starting from 2 samples. In the video, the sample mean is a dashed orange vertical line, labeled x bar. The true mean, set at 50, is a dashed gold vertical line, labeled with mu. The plus and minus sample standard deviations are dashed dark green vertical lines, labeled as x bar plus s and x bar minus s. And the confidence interval is between the two dashed vertical blue lines, labeled as x bar plus lambda and x bar minus lambda. The true standard deviation is set at 10, so 68% of the samples should be between 40 and 60. The statistics tell us that x bar should be close to mu, and mu should be within the confidence interval at least 95% of the time. From n equals 4 onwards, the confidence interval grows narrower and narrower. Notice also that the true mean is contained within the confidence interval at least 95% of the time, but the confidence interval is rarely centered on the true mean. The sample standard deviation shows quite a bit of deviation, for small sample sizes, but becomes quite stable as the number of samples increases. As we pass 50 measurements, note the size of the confidence interval. From this size, it should decrease by roughly a factor of 3 as we pass 500 measurements, and a factor of 10 as we reach 5,000 measurements. Note also the shape of the histogram, which didn't look terribly like a normal distribution to begin with, looks more and more like a normal distribution. The takeaways from this video are 1. When measuring something, make at least 3 measurements, which gives you the greatest decrease in uncertainty per additional measurement. 2. Use the methods in this video to calculate your confidence interval from the estimated standard error and the student's t-value. 3. Report your results with the mean of your measurements, the confidence interval, and the confidence level. For example, 42.000 plus or minus 0.067 at a 95% confidence level. There are 4 additional videos showing how to perform these calculations by hand, with a spreadsheet, using Python and NumPy, SciPy, and using R. Look in the description for the links. Thanks for watching! This video was brought to you by the DOFPro team.